Hello, my name is Dr. Paul Nussbaum, and I'm going to give you a quick tutorial on the operational amplifier, or OpAmp, lab that we're going to do today. So how important are op-amps? Well, let me tell you, if they're making lots of different t-shirts about something, that thing is pretty important. You can see these t-shirts from left to right. The first is a circuit diagram showing that triangle symbol for the op-amp. The second t-shirt shows the popular 741 chip that made the OpAmp so famous. The third t-shirt says overpowered, and many times an OpAmp is difficult to control because it's such a powerful amplifier that, well, we'll learn about that in a moment. And then you could see the last t-shirt, 741, and the other popular 555 chip. We'll be using those in a different lab, but today we're going to use the 741 chip and the operational amplifier. So operational amplifiers, or op-amps, are what we call the perfect amplifier. So if I were going to design a perfect amplifier, it would have infinite input impedance. So even the tiniest signal from a microphone or from a temperature sensor would see basically a very large resistance at the input of the amplifier. So every little tiny bit of the signal would be kind of picked up by that amplifier. Also, it has a zero output impedance, so every bit of power is not wasted on the op-amp. It all goes to whatever it is you're driving, a computer, a sensor, or maybe even speakers in an amplifier system for audio. And then the third thing is that if I were going to build a perfect amplifier, why not just give it infinite amplification? Whatever the input is, just multiply it by infinity, and that's what the output is. So you can see that t-shirt on the upper right that says evolution. That first symbol is for a tube. The second symbol is for a transistor, which was kind of a better version of the tube. And then finally the operational amplifier, which is a sort of the, if you will, the perfect combination of transistors to make an amplifier. The blue t-shirt below it actually has the circuit diagram showing how an operational amplifier is built inside. You don't need to know that, but those are the transistors that make up an op-amp. So are you amped up about it yet? So how does it work? It amplifies the difference between the plus and minus input lines. So sometimes we call it a differential amplifier. So infinite amplification is really not infinite. The output can only go as high or as low as the supply voltage that you provide. And I'll show you how to provide that supply voltage when we do the lab. But still, the amplifier is very, very powerful. So to keep it under control, what we do is we take a little bit of the output and feed it back to that negative input. We sometimes call that negative feedback. And that is like pulling back on the reins of a horse. It kind of slows it down and makes sure that it doesn't amplify too much. Sometimes you might have heard an amplifier amplifying too much and it starts to sound buzzy because it kind of hits the limits of that supply voltage. So we don't want that. We want to keep it under control, and so the t-shirt makes a joke about that, giving negative feedback. So there's lots of ways to use an op-amp. We're going to use them a couple of different ways in today's lab. The joke here is that there's a lot of different ways to use an op-amp, and they reflect a person's personality. So that's kind of strange. But if you give that negative feedback directly from the output, then basically whatever the input is on the plus sign, that's exactly what comes out at the output. And that's the t-shirt that is shown here. It's got the number 1, meaning that it's just 1 times the input. We use that for buffer circuits just to make sure that the input and output are separated from each other with some protective circuitry. But we also have lots of different ways that we can wire up an op-amp, and we'll be exploring a couple of those today. So the lab we're going to do is a hands-on lab. It's called Operational Amplifiers, and here's a photo of that lab. And right on the front page, you can see a blown-up symbol of the operational amplifier is that triangle. You can see to the left of the triangle are the minus and plus inputs, the inverting and non-inverting inputs, or other names we call them. You can also see a couple of sticks coming out of the top and bottom of the triangle, V plus and V minus. Those are those supply voltages I told you about. And then finally, to the right of the triangle, you can see the output, Vout. Now, next to it, in that square-looking diagram with the number 741 on it, that's the pin diagram for the 741 chip. So if you want an op-amp, usually you go ahead and buy a 741 chip, and that's got the op-amp inside of it with wires connecting it to the outside world. Let's zoom in on that real quick, and you can see that there are 8 pins or wires leaving that 741 chip. 2 of them we don't use, 1 and 5 are not used. But you can see that the minus and plus inputs are pins 2 and 3. The minus and plus voltage supplies are pins 4 and 7, and they're purposely kept on opposite sides of the chip so you don't short things out. And then the output voltage is pin number 6. Also, pin number 8 is not connected, so we put an NC there. So really, we're only using a few of the pins coming out of that OpAmp 741 chip. If you were to look at the actual chip, and I've kind of zoomed in on it here, you can see it's got all sorts of numbers and symbols on it. Kind of buried in there is the number 741. The other numbers and symbols have to do with how much temperature range that particular chip can take. Also, what kind of power can it take before it overheats and melts, and they will overheat, and they smell really terrible when you do it. And remember, if it does start to burn and you see brown singeing on it or anything like that, just turn the power off right away. I appreciate it. Also, some of them are radiation hardened for outer space use, so there's all different kinds of other letters and numbers on there that the manufacturer added. But the important one is the 741. And right next to it, you can see the pin diagram that I talked about earlier. So the way to tell which one is pin number 1 is that notch on the top of the chip, and it's also on the top of the diagram. So the pin to the left of the notch, or a little round circle, some chips have a little round circle, that's pin number 1, and then you count clockwise from there to get to all the other pins. So 1, 2, 3, 4, 5, 6, 7, 8. One thing you might not remember is what we call a potentiometer. This has nothing to do with op amps. It's just a circuit element that you might have seen in people's homes as a dimmer switch or any kind of a slider knob. They also make them that they go up and down. But basically, the way that it works is, let's say this one here is a 10 kilo ohm potentiometer. So the circuit diagram symbol for it is there also on the screen. Essentially, if I were to take an ohm meter and measure the resistance between the top wire, the blue, and the bottom wire, the blue dashed, then it's always going to be 10 kilo ohms, no matter what position the knob is turned. So that's why we call it a 10 kilo ohm potentiometer. The knob itself kind of sweeps across this internal scraping area that connects the green, the middle wire, to either really close to the top wire, the blue, or really close to the bottom wire, the blue dashes. Now, I just added these wires myself with soldering. You can see it's kind of a lousy soldering job. But the color of the wires doesn't matter. It's really the 3 wires coming out of the potentiometer, top, middle, and bottom, that you need to be concerned with. So if I turn the knob all the way one way, then the resistance measured between green and blue is 0. And turn it all the way the other way, and the resistance between green and blue will be 10 kilo ohms as I sweep that knob from one to the other. And the opposite is true between the green and the dashed blue. So a popular way to use it is as a variable resistor. Another popular way to use it is to put a voltage across the blue and the dashed blue lines, the top and the bottom. And then, depending on the position of the middle of the knob, the middle wire will have a voltage anywhere from the bottom voltage all the way to the top voltage, depending on the turn of the knob. So that's the way we're going to use it in the next portion of the lab. So I just wanted to refresh your memory about potentiometers. Many times we use these little tiny potentiometers. They can be actually soldered onto circuit boards, fit into small places. So unless you're using a dimmer switch for the home, many times we use these tiny ones. Either one that you have works just the same. Now, when I go ahead and I put items into a breadboard, as far as me personally, I like to kind of line things up so it's really easy to see. My eyesight isn't all that great. So you can see that I've got 3 potentiometers and 3 10 kilo ohm resistors here. And I've gone ahead and put them into the breadboard. So let's take a look at that resistor all the way in the upper left. You can see that it's one of its pins is in a row of holes that's numbered 35, and the other pin is in a row of holes that's numbered 30. Each row of holes has only 5 holes that are connected. So they're not connected across the board, they're not connected up and down, they're only connected those 5 holes together. And that makes it easy, so you don't have to twist the wires together or solder them. It's called a breadboard. In other words, you can quickly build a circuit without having to do soldering. So if I put a wire in any of those other 4 holes in row 35, that's on the same side of that channel there next to the resistor, any one of those 4 will be connected to that left-hand wire of the resistor. And by putting them in the rows that have numbers, it just makes it easier for me to see, but you don't have to put them in rows with numbers. Also with the potentiometers, that lower left potentiometer with the first pin is in row 35. So just be aware that those pins are where the notches are in the potentiometer, not on the outer edges of the potentiometer, just so you know. And those are all 10K potentiometers, and so you can wire them up as needed for the circuit. So as you can see, the breadboard that I took a picture of is inside of what we call an analog digital trainer. So this box is really convenient because not only does it give you a breadboard where you can go ahead and wire up your circuits, but it also gives you the power supplies you need to do all sorts of electronics experiments, including operational amplifiers. So operational amplifiers have to have the input voltage that you want to amplify, but it also needs to have a power voltage, and that power voltage can't just be a positive voltage and a ground. It has to be a positive voltage and a negative voltage. So for all the labs you're going to do today, I'd like you to use that yellow and blue, as you can see in this picture, positive 12 and negative 12. That's how you're going to power the operational amplifier. And as you can see, those posts, the yellow and the blue, they have wires coming from them, and they go right to the OpAmp correctly wired to power up that OpAmp. As you know, you can't play music from your radio unless you first turn on the radio. That turning on means supplying that plus and minus 12 volts. Only after that can you supply the input music, and then it can be amplified. So that's really how an OpAmp works. You first have to give it power, and then it can do the work that you need it to do. When we go ahead and give it input, that will actually be from the 5 volts input line. That's the red screw tab that you can see there. And there it'll go anywhere from 5 volts to ground, that black screw tab on the bottom marked GND. So you can see I've connected those to the plus and minus rails of my breadboard on the bottom. Those rails are different from the other pins I put the resistors and the potentiometers and the chips into. Those rails, anything I plug into that plus rail with the red stripe will be connected to that plus 5 volts. And anything I put into the blue negative rail row of holes will be connected to the black ground 0 volts. So, but by the way, those rails are not connected to any of the other similarly marked plus and minus red and blue rails also on the breadboard. It's just that one row across at the very bottom that they're connected to. So let's take a closer look at those posts where we got the voltage. You can see that if you unscrew them, they actually have a hole in the metal post. So what you can do is strip the wire so the copper is exposed, put it part way through so that it doesn't have insulation in the hole. It's basically just metal. And then screw that down tightly, and that'll make a great electrical contact because the metal will be bent inside that hole and have a good electrical contact. So that's one way to connect wires in your breadboard to those posts. The other way is to use these banana clips, and the reason they're called banana is because they're kind of wider and squishier in the middle, so you can kind of squeeze them. And so sometimes we can use banana clips and just push them into the holes there, and that's an alternate way of going ahead and wiring up your circuit. So this first circuit that we're going to build in this lab is figure 1-2, the comparator. So you can see here we've got the input has got those 2 potentiometers with the outside leads connected to plus 5 volts and ground respectively. and the middle lead connected to, via a 10K ohm resistor, the input of the 741 op amp. So what it's doing, the comparator is comparing voltage 1, V1, and voltage 2, V2, which you can change by turning the knobs on those two potentiometers in the method that I described earlier. So I'm going to change those two voltages in that. You can see that table B all the way on the right are all the different voltages I'm going to try. So you're going to have to use your voltmeter to connect one end to ground and the other one to V1 and the other to V2 and measure the voltages. Turn the knob until you get the voltage you're looking for, record that, and then go ahead and measure the output voltage. You'll find that even the slightest difference between the two voltages will automatically make the output go to one of the two extremes. Now, we're going to not be using 6.25 volts plus and minus. Instead, as I mentioned earlier, we're always going to use plus and minus 12 volts for this particular experiment. So remember that anytime the the power voltage for the 741 op amp says a different voltage, just replace it with 12 volts. And you'll see that the output will try and be infinitely amplify the comparison of the two, but it won't be able to. It'll be stopped at a voltage somewhere before it reaches plus or minus 12 volts. And that's what you'll be recording. You'll see that the op amp can't quite reach the plus 12 volts and can't quite reach the minus 12 volts, but it's pretty close, and you're recording those values. Well, I hope you enjoy the lab. The rest of the lab is pretty much along the same lines. And once you've completed the lab, you will join the ranks of people worthy to wear an OpAmp t-shirt. All right. Thank you for listening. T-shirts are sold separately. Have a great day.